thank you for the invitation and thank you for being here. Not always trivial these days. So I would just like to talk a bit about our work, what we offer, what we do in smart photonics, basically. And I would like to put that in a framework or in a context of using a technology which is actually made for a very specific application, which is usually optical communications, but that can be really utilized in many other contexts. So I just break the presentation down in more or less 3 parts, as I'm just going to give, preach a bit about photonic integration, and then introduce smart photonics and give a few examples about applications. So photonic integration is the counterpart of electronic integration, like a bit more than half a century ago, when people started putting on a planar single piece of substrate many components like transistors, capacitors, and so on. And that really changed since then the way we experience life. Like everyone has today a phone or a computer home and so on. And while photonic integration is not really going to be exactly the same, we were not going to have in our pockets a photonic-enabled quantum computer or something like that, but it will enable a lot, and is enabling these days many applications which cannot really be enabled by electronics. So this is just an illustration of having, for example, a processor from Intel with millions of very basic elements that you need to build gates and do signal processing on the chip. This works. And albeit the scale being very different in terms of number of components on chips, there are several orders of magnitude difference between the two. In the end of the day, it's the same concept as having basically the elements that are needed to manipulate the physical properties of light, being a wave. So you can generate and amplify, you can encode information using modulators, recover this information with fault detectors and so on, and do any other signal processing in the middle of this. Again, very obvious things, but the advantage of photonic integration is really the parallelization or replication of the same concept on the or if you have, for example, a set of components that you need to multiply many times and use them together in one single product, for example, what you would like to do in the end is more or less put those on one single substrate, produce them in a single process, so you can, in the end, just reduce both the cost and the size, the power that you need to operate these devices, but you don't really want to compromise functionality or performance. And this is a very nice example. I will talk about it a bit later, which actually really puts together in one process, application process, and based on standard building blocks. Basically, it's a transceiver with 6 channels that enables more than 100 gigabits per second transmission. So, you have probably already noticed that when I'm talking about this, I'm mostly focused on telecom or datacom. So that's used in access network, backbone, metropolitan networks, or short distance communications for datacom in data centers. But there are many other applications, such as, for example, fiber sensing. So you can use like on-chip spectrometers in order to recover information from Bragg ratings, or even from distributed sensing systems like that are using brilliant scattering and so on. And also these days, a very hot topic in integration is really LiDAR, which is considered a key enabler for autonomous driving or assisted maybe driving. And that is really something that you would like to be compact and cheap, because you cannot buy a car which costs 200,000. Well, some people can, but not everyone. And then also, for example, other medical applications like OCT, optical coherence tomography, where you want to have basically cheap swept sources, lasers without mechanical parts, and that you want to be, for example, in every hospital and not, or even health devices, so you don't want them to be very expensive. Or also gas sensing, something that has already been mentioned. But of course, this may be a bit unfortunate image because I listed 2 microns and not all them mid IR, but there are still many gases which are in the shortwave infrared region, and you can use to detect the absorption peak of those. So smartphone, just maybe a bit about smart photonics itself. So it's a heritage of Philips in the 80s, then it changed hands a couple of times to JPS, Uniphase, to Sedova. But in 2012, it commercialized, being an independent pure play foundry. The photonic integration platform that was developed at the TU Eindhoven, and at first used facilities in Nanolab in Eindhoven. Since then, we have had many multi-project wafer runs, 2015 being the first one. And since then, also 2017, we have our own clean room high-tech campus at south of Eindhoven. And now, after the last investment round, we're trying to ramp up our volumes. The way we're trying to do this, well, we're trying to do this actually in the context of photonic integration with indium phosphide. And we think that's the right choice because, well, if you want actually light sources in the near infrared from about 1.2 to even 2 microns, well, you need indium phosphide. And actually also to date, the most efficient high-speed modulators have been demonstrated in indium phosphide itself. And all these, they do fit in one simple process. You can have both passives and actives. And we also envision that we will be able to have, in the end of the day, because indium phosphide cannot have everything, cannot do everything. If, for example, you want be forming a delay lines of centimeters, well, you need low loss and you need silicon nitride maybe or something like that. So yeah, that's what you need, and should be able to do the assembly. However, we think that this is indium phosphide the right choice because also you can have full-on wafer electrical testing. That means you can also have sacrificial devices, for example, which means that you don't really need to, well, it does not cost anything extra to put them there, for example, and you can really determine at the end of the, well, before the end of the line, how well your devices perform and so on. And all this, we think, is a recipe to enable low-cost integrated circuits. Yeah, the way we want to do this is basically by using a standardized process. And the front face of this is mostly what we call a PDK, a process design kit. So this is just offering to a designer a predefined library of the very basic elements that you can manipulate light, and it can build more complex circuitry with more functionality. So it's more like about having an application in mind and translating that into how it will work on a chip. And you can do that also by using software which contains this information. You can model, and well, you will need, for example, to design something, go back maybe after you have characterized it, have a feedback loop, and so on. You know, not everything is rosy as you have seen before, and it really, even though it is quite mature, it's not really electronics industry mature level. And that infers really that you need to think of what you want to do, you need to design properly, and so on. But all in all, I think the message is that this is through MPW runs, for example, or even maybe for a company, it is financially feasible. It really depends on the model one wants to to pursue, but is really a low barrier to get some proof of concept and then a prototype. So as I said again, just to go very quickly, you can just put these very basic elements together. So these are just waveguides. You can do routing. These are well characterized in terms of losses and group indices and so on. So you can have a fairly predictable behavior. You can have phase modulators, and recently we have also demonstrated up to 30 gigahertz modulation bandwidths, and also optical amplifiers, which are really unique to indium phosphide. So that's I think the strongest suit of the material itself. Then also flow detectors, of course, either DCS monitoring and high speed for the receiver side, for example, if you have a link, or EAMs for short reach communications if you would like to do. Or actually, I'm really well. It's really nice always to see that such a building, for example, can really be used as an absorber, so saturable absorber or something else for like a differential absorption LiDAR or something like that. And of course, grading tool can be used either for, well, mostly for lasers. You can build your own laser, really depending on what you want to do, or some filter. And these gratings are also, I should say, it's yeah, they're lithography defined, so that's really nice as well from a technology perspective. And well, many times there is a lot of, well, for good reasons, but there is a lot of fuss about costs and so on. But and there is an argument that always, you know, indium phosphide does not scale. Well, it's true, it does not really scale. You are not going to go to 30 millimeter to 300 millimeter wafer, but as in silicon photonics. But first of all, that's not the point, because probably there is no market really that supports a 300 millimeter wafer for photonics in general. So that's not what you want to do. And secondly, that's not really telling the whole story, because in a product you don't care only about the cost of a chip, but you care also about the packaging and the assembly. So there are more things to consider than just the cost of the chip itself. And again, if you want, well, you do want mostly light generation amplification and modulation. So this is really intrinsic to material itself. So that's implies that, for me at least, is indium phosphide is a material of choice for this. And maybe a nice example is talking about a bit, but a fairly complex module that is something that people are really interested these days about coherent transceivers, is that, you know, you need to have lasers, especially low line width lasers. You need to have IQ modulators, which are already, well, you have high speed phase modulators in there. You have couplers, you have DC phase tuning, for example, phase shifters, and so on. And then you have on the receiver side, you have balanced flow detectors and so on. But you know, it's a fairly complex circuit. But in the end of the day, you will see that what really costs a lot and is really taken out from the cost if you use indium phosphide is the assembly. So you don't really need to have everything on different chips and put this in a gold box and have a lot of micro optics and so on. Well, some of them will be there, of course, but still the cost is really reduced. And then just to switch a bit gears, well, well, I have been only talking about optical communication so far mostly, but the purpose of this presentation is really to kind of demonstrate that even though those are the biggest markets and the biggest drivers for the technology development, and that has been since, as was mentioned before, since the 60s, since the invention of the laser and then the EDFAs, the low loss fibers, everything has been driven by optical communications. But well, a lot of other applications out there are benefiting from that to this day. And you can use such a technology, which is at this point really a general purpose one to build different electrical photonic circuits. And in all of these, I think, well, not all of this actually not true, but in most of these, what you really need are lasers. And typically these days, what you need is you need tunable lasers. If you don't have an integrated one, you're going to have something like this. You're going to have just a reflective SOA. You need basically some gratings or mirrors which are mounted on piezoelectric, on piezoelectric elements, and all this basically already suggests that this is just a module and cannot be integrated. But using indium phosphide, for example, you can have this or arrays of these lasers with similar characteristics, like covering at least a whole C-band or other wavelengths, depending on the material gain, and also line widths which are reaching down to 100 kilohertz. So this is a fairly old example now. This is 2015, but I always like it because I think it really suggests that, well, if you have the imagination to put something together to solve a problem, and also you do proper simulations and calculations, that can really lead to something which is manufacturable, and you have a fairly predictable behavior. So this laser is already, as I said, quite old now, maybe, but it has a very good, it has, I think, very good performance sort of tuning range and line width as well. Another example is, well, it's again a ring cavity, but it's a very classic one from silicon photonics, where you have, or silicon nitride, what Guillermo showed before. There's slightly different geometry, but this is monolithically integrated, and you can have good side mode suppression ratios of single mode operation. You can tune over the C-band. Of course, that really depends on the choices you make when you design such a laser. And you can have electro-optic tuning here, which means basically not too much thermal dissipation. You can do fast switching. That's usually depending a bit on the laser geometry, but it's typically, for example, something like the 10 of a nanosecond or something like that. And also over the tuning range, you can have a fairly flat intrinsic line width. It's around 100 kilohertz in this case. And yeah, of course, not everyone needs a widely tunable range laser. So you can have just simply DDR lasers by putting together some DDR mirrors and SOA phase section and so on. Just now going to application side. Well, a pretty typical example of today's is really some either dense or coarse WDM system. So you would like to have multiple lasers of different wavelengths on the same substrate, each one attached, connected to a modulator, and then you would like this to be, for example, it could be in a protocol network, so leading to some antenna towers. And this is the example I showed before. This is designed by Wiming Yao from Eindhoven University. This is a very nice example of what you can do without even designing a single building block and using what you can have. But it really takes a lot of effort, of course, to know what the limitations are in terms, for example, of what was mentioned before for crosstalk or all these things. But the results were really nice because you have already on a standard cell size, which is less than 25 square millimeters or so. You have 6 lasers, which are over 20 nanometers tunable, and each one comes with a modulator, so you can have a 6 by 20, so that's an excess of 100 gigabits per second modulator, transmitter on a single die. And you could think of doing the same thing basically on just using, depending on the application, or with the AMs, which can have standard building blocks up to about 50 gigahertz bandwidth or so. And this is an example. This is just a solitary modulator, actually not like an array, but you can do, this was demonstrated up to 112 gigabits per second, I think, up to how much? 1.5 kilometers of fiber. So that would be something that could be used, for example, in a data center or so, or some short reach communication. Then gas sensors, has already been shown here that you can do absorption spectroscopy, for example. You can do it in different ways, but what I'm going to show is just the simplest one, just scanning a line on top of an absorption line of a gas. And as I said, okay, many gases are actually in much longer wavelengths, which are not, which means basically you use a sort of different material system, but there are still quite a few gases which are interesting, and that's in the short wavelength infrared range. And just a couple of examples. So this laser actually is what I showed before, but it was also demonstrated as an acetylene sensor passing through a gas cell. So instead of having just a bulk laser, maybe a spectrometer, because in this case the spectrometer actually is not really integrated, I think, but you can also do that, as I showed in the next slide. But you can see that you can really see the absorption line of a gas. And I think it was mentioned before that these lines are pretty narrow. Well, I mean, a gigahertz is typically, I think, considered not extremely narrow. So it's actually the line which is much narrower than that. So I think in that sense, the line width of a few hundreds of kilohertz is already very good for that. This is another example for ammonia sensing. So it's a hollow core fiber. I forgot the word here, but this is just a reconstruction basically. So it's an on-chip laser, it's an on-chip photodetector passing through a fiber which is filled with gas, and then you can reconstruct the absorption line around 15-22 nanometers or so. Again, of course, the system you are using really depends on the concentrations that you are after, how many parts per million or billion you need to do. So that defines basically your application and your circuit. And you can do very different things. Also, you can do, for example, dual comb spectroscopy. In such case, you really need a dense comb. This is a 2.5 gigahertz repetition rate. I will show another one later, which is even more dense. But this was designed specifically actually for gas sensing. Another application, another example is basically interrogation of fiber Bragg gratings. So on a fiber, you can have multiple gratings of periodic structures at different wavelengths. And if you shine light, that can be either a broadband source or a swept source, or like a single mode laser. And then you can have, if you collect the reflection of those, you can distinguish with a spectrometer which are the resonant wavelengths. You can always see basically and convert those shifts to either strength or just optical path length change or temperature change, or both at the same time for that matter. And I guess a success story of a Dutch company is it's called these days called Photon First. It's a previously called Technologies, but they're really commercializing photonic integrated spectrometers basically. So they're reading out fiber Bragg ratings, and they're really they do basically massive parallelization of all of these Bragg ratings. So they have a lot of them in a fiber or multiple fibers, and then basically they can read out with picometer accuracy and resolution the strain which is applied on it can be either man-made or or natural structures. So you can have basically structural health monitoring systems. Another example, which is was already mentioned, is the microwave photonics or terahertz photonics. So, and that is just driven by higher bandwidths, and also you want to distribute or even process microwave signals in the optical domain. So this is courtesy of Guillermo again. This is just the denser comb that has been demonstrated so far, monolithically integrated, so 1 gigahertz. So you can also want to have maybe, for example, also space applications, really RF sources, which are light and can withstand radiation and so on. Or you could do, but it's a very, it's not the most elegant example, but it's a very straightforward one. How you could do, for example, bidding of 2 lasers in order to generate a terahertz node, and you can of course improve in many different ways by phase lock loops or offset locking and so on. And there are many more applications. Such as ladder we're working on. There's integrations that would be, for example, for optical phase arrays. You want to have typically in automotive industry. I have time actually. Okay, I will stop. But yeah, for automotive industry, hundreds of elements and so on, and then also for imaging. And we are also I'm very excited to be working on this, because we're trying to also transfer everything to 1300, and I think that will be additional value, because then there are actual applications which are more suited for different wavelengths and so on. So yeah, just a summary. Basically, that we think that photonic integration and our open access platform basically is an enabler, it's a low threshold for companies and research institutes or universities to start prototyping photonic integrated circuits, and we can make that happen to scale. But thank you very much for your attention.
Thank you very much, Stefanos. Now we have time for some questions. Anyone is ready to do?
In the LiDAR applications, you need detectors, because that's right now. And in silicon, we have a SPAC, which is single photonic range detectors or diodes, or you got silicon LiDARs, which is also connected in a way that is like
Yeah. You can have that in the first side as well. Oh no, we don't. No, we don't have it, but you could have it. So first of all, silicon, not single photon detectors. Those are usually different type of devices, and they also operate in cryogenic temperatures. So that's a different game, I would say. But yeah, avalanche photodiodes, indeed. For example, you can make them in both. In silicon, they're just not in a generic technology. No, that's not compatible at the moment. But in LiDAR, for example, you do actually what you need is a coherent detector. Yeah.
So you thought that 20% is something of radiation, but some of your devices. Do you have any other information about the radiation tolerance of the?
Yeah, we have. Yeah, I don't have numbers on top of my head, but there are a couple of projects that we. Well, there should be some numbers. So if you're interested, you can just email me. But I really don't have numbers on the top of my head.
Could the publicly available?
Oh, publicly, yeah, I think so. Well, yeah, if you ask, you would probably yes.
Thank you.
Any other questions?
First of all, congratulations on what you're achieving. It's fascinating.
We saw in the presentation from Guillermo that the indium phosphide is the technology of choice for generating light around up to 50. And in the presentation, we see that we should have all photonics phosphide in one chip, and that's why photonic integrated circuit using indium phosphide is the choice. Being one of the unique boundaries in indium phosphide photonic integrated circuits, would you comment on the market size for both? How many of your customers, potential customers, come to you because they want a game chip, and how many of them want a full feature photonic integrated circuit?
Yeah, I'm not sure how much I can comment on the percentage of. Well, I can answer differently, I guess. I can say that indeed there is also interest for just gain chips, and as for example, it could be. I mean, if you go for something like that, it could be another kind of a different story. You might have, for example, buried heterostructures that we also do. But indeed, there is interest. So it really, but it depends on the application. Yes, there is interest. That's all I can say, I guess.
Most of the companies who are targeting the chips, the first one, they end up that they don't have enough volume to go to the more indium phosphide foundries. And there, usually there is a value for a foundry that can target smaller volumes, like microphone.
Well, there is, so yeah, well, currently the, yeah, I think so. I think that it is, well, the volumes that are usually asked are not too far from what can be offered in the very near future, actually. And then, well, at the moment we are working with the 3-inch wafers, but we're also our fab is enabled for 4-inch, so that really scales up quickly. Yeah, I think that that's the size that can serve the market at the moment.
Okay.
Thank you. Okay, thank you.